Hello, everyone. Welcome to Stage of Java. And today my talk is on Java is fast if you don't allocate too much. Um, who am I? Well, I'm a Java champion and I have 13,000 answers on Stack Overflow. I was the first gold holder for memory, file I/O, and concurrency across all languages, which gives you an idea of my area of interests. And I'm the CEO of Chronicle Software. I've also got a blog and a number of talks. I've been working with Java for 25 years now. Um, so why is it I'm talking about allocations instead of GC pauses? Well, the thing is, well, the JVM will measure GC pauses for you because that happens in a particular cycle. It pauses the application, does a GC, and then lets the application resume. Allocations don't show up as obviously because they happen incrementally as the program is running. And you don't get a running total of how much was of my throughput was lost because I was allocating. And as you will see, I have some examples here where the cost of allocating short-lived objects, at least, was around 80 times higher than the cost of cleaning them up because, again, if they're short-lived, there's actually very little to do. So in that case, the GCs look like there's little impact, but in fact, the cost of allocation was significant. Another problem is that this doesn't show up with single-threaded tests so much, and I'll show why that's the case. And in fact, even if you're using 2, 3, 4 threads, there's a good chance that allocations don't show up as being a problem. But if you're running on a server with more than 4 cores, not just a virtual machine, but the physical machine with more than 4 cores, at that point, if you're trying to use the whole machine efficiently, allocations can show up as a real problem. So if we have a look at, so this is a benchmark you can run. I've provided the details a little bit later. If you're allocating many small short-lived objects, the cost of allocating them is very low. So that's why generally the wisdom is that allocating an object doesn't cost very much. And in particular, even up to 4 threads allocating objects, the cost of allocating each one of those objects is very small. It's in the tens of nanoseconds, which you would think, okay, well, that doesn't really make a difference. The problem is that as you go up with the number of threads active on your system, the cost of allocating increases as you go up, particularly for larger objects, but even to small objects, the cost increases. And that's because what's happening is that you're saturating the memory bandwidth, the ability to scroll through memory, creating more objects for allocation. And that saturation point is reached quite quickly. So you're not making full use of all of the CPUs on your system because you're drawing on this contended resources, which is your memory bus. The reason for this is that if you look at the CPU layout of these are obviously simple CPUs. These days, you've got much more cores. But nevertheless, each one of these cores is hitting a shared contended resources, which L3 cache, which is your level 3 cache, and also your memory controller. So newer high-end servers will have like 4 memory controllers and maybe 2 or more L3 caches, but you have essentially the same coordination problem that once you go beyond your cores L1 and L2 cache, you're hitting shared resources. That means that when one core is busy, it can get in the way of another core. And certainly when you're trying to use 16 or more cores at once, you want them to interact with each other as little as possible. And just allocating memory is one of the ways you're forcing an interaction by drawing on the main memory, and essentially causing a bottleneck. So so the benchmark's open source. You can try this out for yourself. What do the data structures look like in these tests? Well, we use a YAML test for our microservices. That's YAML data in and out. The actual low-level format in binary is much more efficient than this, but for testing purposes, it's easier to mock up YAML tests. And as you can see, we use nanosecond resolution timestamps. We use, instead of using strings in many short strings, in many cases, we replace those with a long for efficiency purposes. So these data structures are only 44 bytes in reality, which makes them really compact and use less memory and less bandwidth. But nevertheless, if you do enough of these, it adds up. And a very standard testing methodology we use is testing round trip time, either for latency or for throughput. In this example, we're using up to 16 clients connecting over TCP to a echo service. And this is the code for the echo service. It gets a top of book event with a top of book object that's been deserialized. And all it does is it sends it back to the original receiver and the original sender, so that it can then do a timestamp saying, well, this is how long it took to do this round trip. Now, for the purposes of this benchmark, you can optionally take a copy. And what that does is it triggers it to create a new object that gets retained. And this is where the allocations come into it. So for each one of these messages, I'm creating just one small object, which is obviously you're not going to be doing the message rates here. It's just generating a load created by allocations. How much does allocating a few objects, or even just one in this case, matter to how does it impact my throughput? So if we're just allocating these objects as quickly as possible and not doing anything else, just to see how much my allocation pause time is, it starts off very low, around 15 to 18 nanoseconds. But you can see as you go beyond about 4 threads, what happens is the number of objects being allocated per second doesn't really increase. Instead, the average latency increases. And whether I use 2 JVMs or 1 JVM on the same machine doesn't make any difference. The time to allocate just goes up. And this bears out in the benchmark I just showed you. This is doing now round trip time. It's using TCP, it's using serialization, deserialization, all of that's other work. But so in amongst all of that, what difference does just creating one object make? Well, in Java 11 at least, which is faster than Java 8 for this benchmark, but in Java 11, we're getting 67 million events per second. That's over 4 billion a minute on a single machine. So obviously that's a lot. The average latency then is around half a microsecond. And what's interesting is that the difference that just allocating one object makes adds in the order of about 150 nanoseconds, as we saw from the previous benchmark. It's actually slightly higher, but it gives you an idea that of how much difference adding one object makes. Now, it's much more obvious when you look at the throughput, because the throughput has dropped by 25%. So when I ran this benchmark, only 0.3% of the time was spent in GCs. So if you looked at the GC log and said, well, it's only spending 0.3% of the time GCing, I don't think allocations matter, or certainly GCs don't matter. You may actually be missing out on the fact that, well, actually the cost of allocating those objects in the first place is 80 times bigger. It's about 25% of my throughput is now being lost to allocations. So here's another benchmark I did, this time on a new laptop I got. Just for comparison, this is running Windows. The other one is a high-end Ryzen running Linux. But you get a very similar sort of result. So this is the throughput that you can achieve on this machine. And you'll notice that for 1, 2, 3, and 4 threads, clients in this case, the difference between whether you allocate or don't allocate doesn't really matter too much. There is a little bit of an overhead, but not so much that it's possibly worth worrying about. However, as you try and scale beyond for clients in this case, um, you just it just doesn't go any faster. As you add more and more clients, you're not getting any more throughput. In fact, you get a slight dip in throughput. However, in the allocation free example, the performance, the throughput continues to go up, not dramatically, but it does go up. And the gap between what you can achieve with allocation free and even a low allocation rate widens significantly to more than 25%. So here's, in this example, there's quite a drop in terms of the throughput you can achieve at 16 clients. So is there any simple way to test this for yourself without doing all of this analysis? Well, it turns out that most modern machines, from laptops all the way up to servers, have a similar rate at which they top out in terms of allocations. And this is the total allocation for the physical machine. That's all the JVMs across every virtual machine, across every container, all combined, sharing this memory bus bandwidth. And that's somewhere between 10 and 15 gigabytes per second. So you can look at, you can add up all of the JVMs on your machine, what's their average allocation rate. And if they're sitting at a very constant level, even though the load might be varying, that's a significant hint that allocation rates are your limiting factor. It also means that if you optimize any one of them to reduce the allocation rate for the whole machine, so you don't even have to optimize every one of them, but if you optimize any one of them to reduce your overall allocation rate, or perhaps if that's not an option, redeploy it to another machine, then you can increase the throughput that machine can achieve. And you may even find that after optimizing it, the allocation rate doesn't go down, but the throughput that machine can do goes up. So in summary, one of the key takeaways is that if you're trying to use more than 4 cores at once, have a closer look at your allocation rate for the machine overall, because it's not the GC pauses that may be, GC pauses can be impacting your latency, but the allocations can be impacting your throughput. So on a related topic is accidental complexity. Now, that's the difference between what is essentially required to fulfill the business logic and what is additional complexity that isn't actually required. So in this example, where I'm talking about allocations, the allocations are having an overhead, measurable overhead, without necessarily fulfilling the business logic. And so that is an example of accidental complexity. There are other kinds of accidental complexity, but allocations are the ones that tend to stand out, particularly in the low latency trading space, which is where most of my clients are. So to give an example of accidental complexity, I'm talking here about looking at a benchmark, which is another blog that I have on my website, about comparing Kafka to Chronicle Q. Now, both of these are designed for low latency. They're both written in Java. And in this case, what I'm doing is I'm benchmarking how long it takes to send a message via a queue to a microservice, have the microservice reply back to another queue and return. So it's similar to the Echo service, except there's now 2 hops because it's going via a queue each way. However, the important thing here is that the latencies, even though they appear very small, and in this case, it's about 2.5 milliseconds, which is about half of what most published benchmarks for Kafka suggest on the 99th percentile. So, I got what might be considered a good result. 2.5 milliseconds, to put in context, is less than a tenth of what you can see. So even at 25 milliseconds, you can't actually see that For example, movies traditionally had each frame was only 25 milliseconds apart. You couldn't see each frame changing as it changed. So 25 milliseconds, the flicker is too quick for you to see. So 2.5 milliseconds, a tenth of that, is much faster again. So it's faster than you can see. So you might think, well, why would I worry about that? Well, one way to think of it a little bit differently is to think about how far could you send a signal in that time. So turn it instead of from time into distance. So this is sending a signal from New Haven down to Washington is about the distance you could go in 2.5 milliseconds. So it's a fairly long physical distance. So you can imagine having to walk that would take a long time. This is using Flight Recorder. In this case, I was benchmarking the client. I wasn't benchmarking the broker. The broker probably produced about the same amount of garbage. And you'll notice that it's sitting at around 12 gigabytes. For whatever reason, each of these bars is 2 seconds wide. So in fact, it's 12.5 gigabytes every 2 seconds. But like I said, it wasn't including the broker. So it could well have been about 12 gigabytes a second, which is similar to the previously mentioned limit for how much you might be able to get in terms of allocations. You'll also notice that it's G-Sync a lot. Down the bottom, you can see it's G-Sync quite heavily. And in fact, you can see that the heap size is a gigabyte. So if it's creating 6 gigabytes a second, then it's G-Sync at least 6 times a second, which is quite often. Certainly for in mouse space, in training space, at 6 times a second is extreme. So to give you by comparison, I'll show you in the next slide. So the latency for Chronicle Q to do the same task, put a same message into a queue, go to a microservice, have it come back again, including serialization, deserialization, all of that, is around 3 microseconds. So that's about 700 times faster. Fairly significantly faster, and yet it's doing the same work for at least for that benchmark. So the difference between what that solution does and the other one is entirely accidental in this case. So most of it is an accidental complexity. In fact, it's more than 99% accidental. Only less than 1% is actually doing the task that's required. Excuse me. And not surprisingly, given what I've talked about, the GCs are extremely low. So as you can see at the bottom, the memory usage, it's on a scale of 1 kilobyte. Not sure why. But the allocation rate is very low. And the reason there's any allocations at all is, in fact, that Java 8's flight recorder did create some garbage when it was running its samples. Java 17, however, does not do that. And then you can't see anything at all. So there's nothing to even look at. But in this case, even with flight recorder creating some garbage, when we're only at about 320 kilobytes per second. Now, one thing to note is that when I ran this benchmark, Chronicle Q was doing 5 times the load of the Kafka benchmark. So even at 5 times the load, it's G-Sync or creating so little garbage that it's not even really able to record it. So how do we plot the differences but in latency? That's rather a difficult task. We can turn it into lengths to try and envisage it. In this case, it's using a logarithmic scale. Logarithmic scales are hard to interpret because people aren't used to reading logarithmic scales, but you can see that down the bottom on the 99th percentile, the Q Enterprise is sitting at about 3.7 microseconds to do that entire round trip for the 99th percentile. The open source version is around 31 microseconds. The Kafka is sitting at about 2,633 microseconds. And if you increase the throughput up to 250,000 messages a second, it goes all the way up to 285,000 microseconds, which is very high. That's probably beyond the load of what it can achieve. But you can see in particular that both the open source and even in the commercial version have very flat and low latencies. And the difference between those is the accidental complexity. And one of the keys to reducing that accidental complexity is reducing allocations. So lastly, just looking at the ratio of latencies, I'm pointing this out because it was actually surprisingly consistent across a range of percentiles, that it's sort of sitting around 750 times. Again, like I said, it's about 99.98% of the latency is accidental in this case. So we have some time for some questions. This is the bit where I start talking live. Thank you very much.